And now we look forward to listen to Kuda for paleontology in Africa. Over to you, Kuda.
Okay, good afternoon, everyone. As already introduced, my name is Kudakwashe JAKATA, and I've just started a postdoc at the European Synchrotron Radiation Facility, the ESRF, in France, Grenoble, working at BM05. And today I'm going to speak on paleontology enabled by synchrotron light sources. Okay, so I think in paleontology, what's really important is, so what usually happens is that the scientists go out to the field and they look for fossils. And when they found them, they bring them back to the lab, and they really want to study these animals that they've discovered. They want to figure out how they behaved, what they ate, what their environment looked like. And one particularly interesting goal is that you don't want to break the fossil, because this is our heritage, and you'd like to keep it so that in future generations can also be able to study the same specimen, and possibly with newer and better equipment where they can actually make more discoveries which are not possible today. And so that's why it is important for us to actually not destroy our heritage materials, including paleontological specimens. So tomography is an X-ray based technique which is very useful for this kind of thing. So a typical tomography setup is that you have an X-ray source which produces an X-ray beam, as shown here, and then you have a sample on a rotating stage. So it is rotated, and as it is rotated, you acquire projections or radiographs at various angles as you rotate this the sample. And then the samples, the radiographs are then reconstructed using several algorithms which can be used, such as the filtered back projection and iterative techniques that are also available to then produce a three-dimensional image, which allows you to look inside and actually view the anatomy and of a fossil without destroying it. So you can now do this virtually on your computer. So also at particularly at synchrotrons, although this is also, you can also do this in a lab-based tomography setup, is that you can obtain phase contrast imaging. So this phase contrast, which gives much better contrast and is also like much far more sensitive to sample inhomogeneities. So for example, here, using absorption contrast, this is a radiograph showing absorption contrast of a sample of amber, which is opaque amber. So this would absorption contrast would have been like very tricky, and one can sort of see sort of lighter regions, lighter colored regions, and darker regions, and but you can't really make out any features objectively. But then the same sample, when it is when you take a tomograph using phase contrast, look what you see. You actually see two insects here and more features actually in the same sample, which is quite, I would say, quite impressive. So one would say that absorption contrast shows clearly the difference between is far better and very useful. I think if we, this is just a video showing the same sample, and now looking at the tomography, and once after the segmentation has been done, you actually see that actually the all the bugs or insects that are inside. And this here is sort of the BM05 where I'm working. So this is the old BM5 before the ESRF was upgraded. So it starts from a bending magnet. The X-rays pass through some filters to increase the average energy, and then the X-rays pass through the sample, and then you get to the detector. to record the radiographs. So that's the detector over here for recording the radiographs. And this here is the sample, which is on a rotating stage. As we can see, the sample being rotated. And of course, the filters to increase the average energy, and the chopper to reduce the power. And of course, the bending magnet before, yes, the bending magnet. So this is what BM05. Of course, the upgrades have made it different, but I'm not going to show the front end. So after the upgrades and the current status of the experimental hatch at BM05. So over here, this is the sample stage with a sample in a tube over here. And so the sample stage allows translations and rotation. And these are the detectors, the two detectors, which you can automatically just by use of a few commands sort of adjust. And this allows you to change from something like 25 microns to 1.3 microns automatically. So this is what BM05 is like at the moment. And so just to give some examples of paleontological specimens that have been scanned at synchrotrons. This here are dinosaur eggs. These are dinosaur embryos. So these were discovered in South Africa. And dinosaur embryos they're among the rarest fossils that people can find, and they provide a unique window into the paleobiology of these animals. I mean, you can start thinking about quite a lot of research ideas. Like one can ask whether, if you wanted to find out whether this particular dinosaur, when it was born, did it require a lot of parenting or not? Whether it was born with teeth or without, those kind of questions. In order for you to study them, you need to actually extract the embryo outside of the fossil. And this is enabled by synchrotrons, actually, and X-ray tomography. So actually, so this egg here, this particular one was prepared in Canada. And yes, with sort of mechanical preparation, which is still very helpful, one can expose the sample. But then with X-ray tomography, then you can actually now see the actual you can now see the various bones that make up the fossil. This here, so this particular embryo is of a dinosaur which is called a Mesospondylus, which is so there are quite a number of adults which have also been discovered in South Africa. This is a juvenile Mesospondylus skull that has also been CT scanned and actually segmented, and you can see the various features of what it would look like when it was older. So a group of researchers from Wits University, the Evolutionary Studies Institute, they did research on this, led by I think Kimberly Chappell was working on this, and they observed now generation teeth which get resorbed or shed before hatching. And their study has allowed it has allowed them to come up with a method that can be used to assess the developmental stage of extinct in vivo saurians. And this research has actually been published in Nature Scientific Reports, and it was published this year. And if you're interested, you can actually go and have a look at this publication. Very interesting research, I must say. Something else that can also be done at synchrotron light sources in paleontology. Here, this is research that was done by Paul Taffaro. So this is the first experimental publication on a South African hominid, and it was the first demonstration of virtual dental histology. So what was done in this case is that they took the sample, the actual sample, and they did tomography at the synchrotron of the whole sample, and then after that, the sample was then taken to the lab where a histological section was cut out. And after the histological section was cut out, then they looked at it under a microscope. And when you compare the two, this is this is the histological section that was from the microscope, which is at about 30 microns. And below, this is the tomography at the same position where the histological section was obtained. And one can actually see the accuracy and that you can get from virtual histology. And so if you then superimpose the two, so this is a superposition of the two, the yellow or brown sections. These are the sections that are taken from the microscope, and the gray in the background is the virtual histological section, and one can see that actually this is very accurate. So this was actually a development of a method that could be used to analyze teeth, and one can actually clearly see how accurate it is, and this actually demonstrated the accuracy of the technique. This was then developed, and it was then used. This is Anyanzipithecus alesi from Kenya. It was about 30. It's about 13 million years old. It's the most complete Miocene ape cranium yet known, and the age at death could be determined with incremental lines. So you can actually see it's very complete. You have the inner ear, which is preserved, and if one looks at the inner ear, one could actually determine the posture. And when you look at the teeth, again, looking at the research that was done by Portaferro, and with the sort of at high resolution, you can be able to actually see the incremental layers, which will allow you to determine the age at death of this particular specimen. I think they found the age at death to be just above something like about 300. 400 days old. I think I'm not very sure about the age at death, but yeah, it was found to be somewhere around above 400 days. And here is the technique. So Portaferro, again at the ESRF, they went on to to develop the technique further at looking at these incremental lines. And what you've seen before is that the virtual histology was being done using two-dimensional sections, but the technique was then further developed so that one could then do three-dimensional sections, which is actually pretty more impressive. And I think this is a very good demonstration also again of how a synchrotron light source in Africa could actually facilitate in people, scientists who would be working at this particular facility can then develop methods that can be used to access things that may not be accessible today. Research questions that may not be able to be asked today can then, as people work and develop techniques, they can then improve on the techniques and ask more questions and reduce the limits to the research and questions that can be asked, which is quite which is what we really hope for. Again, Anna, moving a little bit further, but still remaining with teeth. This is Moschops campensis. It belongs to a family called Dinocephalians. I think they existed over 200 million years ago. So this is a skull that was sort of scanned at the ESRF again. And here at this particular point, the study was looking at tooth replacement. And you can actually see the erupted teeth here and the unerupted teeth here. So one can then figure out how this particular specimen used to replace its teeth. This study was done by Luke Norton, also at the Evolutionary Studies Institute at the University of the Witwatersrand. the name of Moshops, it actually translates to terrible head. And so later on, about 10 years later, another researcher from Wits University so initially looked not on only only did a tomograph of the sort of half of the specimen. And then later on 10 years, Julien Benoit scanned the other half of the specimen when he was again doing sort of further studies of the Moschops capensis, which and he found that it had a body weight which reached up to about 1 or 2 tons, and the brain the size of about a chicken egg. And the Moschops brain was probably one of the smallest among its contemporaneous species. And also the anatomy shows that the male Moschops was sort of ramming. They were ramming into each other like giant overweight goats. So that probably explain why it evolved to have such a big sort of head and terrible skull. So as you can see here, you can actually see the internal structures of both the pieces when they are put together, the two scans, which are sort of separated by 10 years. Okay. And so this is also the publication from Julien Benoit and his collaborators on the Moschops capensis, which actually makes for quite some interesting reading. We move on to another specimen, the Heterodontosaurus, which has been studied by Victor Rademacher. So Victor Rademacher, this is where the specimen was found in the field in a slab of rock, and it had to be cut out of the slab, and so you get these pieces where after it was extracted from the rock. And and then after preparation, so again using mechanical preparation, and this is actually beautifully prepared. You can actually see quite a lot of the specimen. But however, to view the internal anatomy and also there still remains quite a lot of it that is sort of buried inside the breccia. So one has to do a little bit more, and so it was taken. So this is what the Heterodontosaurus probably looked like. An impression also done by Victor, who happens to also be an artist. So after tomography was done at the ESRF and segmentation, this is what was this is the specimen after the after extraction and segmentation. And so just showing it in a movie, you can actually see the limb bones, and one can actually see also the sort of gastralia and the ribs and sort of all the features that are in this particular specimen. And what was interesting about this particular specimen when it was studied is that actually the synchrotron CT, when you look at this cartoon, it revealed structures that were not known before to have existed in this particular specimen, which are these gastralia here, these sort of things that look like the blue and green things that look like tennis rackets, which are sort of which are thought to have contributed to the breathing as they are sort of attached to the diaphragm. So the paper has been written, and it's currently in review. So please watch out for that, and I think it will also be make some very interesting reading. Then again, there is research that was done on an Egyptian mummy. So here, this is a movie which shows sort of an Egyptian mummy after. So this is sort of radiographs, 2D radiographs as you go through it. So this is the mummy as you segment out the sort of the cover, and one can see the cloth that was wrapped around the mummy, and you can then virtually extract the skin and leave out sort of as you extract layer by layer, and you can remove sort of the end up with the bones only. And when you look at the head, you actually see that here it was probably someone hit it on the head, and it looks like that is the probable cause of death. It is this mummy, I think the research on this particular specimen showed for the first time that actually there were some mummies, because the Egyptians probably kept farms of they kept farms of crocodiles for mummification, but this is the first demonstration that actually they also did some hunting. And here you actually see some of the stuff that here is, one could actually look into the stomach and find sorry, I've just lost myself here. So if you can just give me a moment. So one can see what's the crocodile had eaten just before it died, when you look into the stomach, and it's one can see that there were some. Just wait. Okay, so that's the probable cause of death. It was probably hunted this way by hitting on the skull, and when you go into the stomach, then you can you find what is the contents of its last meal. And here are the contents of his last meal. So you find that there was a feather, there were some eggshells, and there is also a rodent inside. So this actually gives sort of evidence of what its possible diet was. And one can then go ahead and try to reconstruct what the environment looked like, what animals lived in the environment that it was in. And again, one could then zoom in and actually look at the teeth, which this enabled the identification of the rodent, where they actually identified the genus of the rodent that was inside the crocodile, the mummified crocodile. There is a new development at the ESRF, the building of BM18. So these pictures are just showing the various stages of the construction, which it has started. And actually, the construction phase has moved beyond this here. And I took some pictures this morning in the rain, and so yeah, this is what it now looks like. So the hatch is completely finished, and now there's work inside. I tried to take pictures inside, but unfortunately it was locked and I couldn't enter. So this is sort of a movie of what is going to look like when it is complete. So this is the experimental hatch for BM18. So BM18 is going to be sort of quite an extraordinary tomography beamline, which is going to be able to, where it will be possible to do a complete tomography of an object which is up to, I think, about 2.5 meters long. And so this is the sample stage that you see here. And this sample stage will be able to take something that is of the weight of about 300 kgs in weight. And this, in comparison, you can see here, this is the size of the sample stage at BM05, where I am at the moment. And sorry. When you compare the three, so this here is the sample stage at BM18 when it is complete. This is what it's going to look like compared to the size of a human being, and compared to the current sample stage which we are using at BM05. I think this gives you sort of a very good impression of what this is going to look like. So it's going to be a very versatile beamline. which is going to cover a voxel size from 0.7 to about 100 microns, and an energy range of about from 30 to 350 kilo electron volts. And as I've already mentioned, it will take something up to about 300 kgs in weight. And it's going to have the highest level of coherence worldwide for on a large beam at high energy, which will also allow very low dose imaging when it is required. So this is going to be a sort of a giant leap for tomography and for heritage specimens. So to end my talk, I'd like to thank my colleagues at the ESRF at BM05, and I would also like to thank the people at the Evolutionary Studies Institute at Wits University, where I was before I came here. And I would also like to thank these organizations, the European Synchrotron Radiation Facility, the African Light Source, for giving me this opportunity to give the talk, Wits University and the ESI and the Center of Excellence in Paleo Sciences at Wits University. So thank you very much for giving me the time to give the talk. And by the way, actually, this is another specimen also from the from the ESRF, where you have a trinoxodon and a bromistega, which were found in the same particular specimen. And this was just quite unique and very interesting. Thank you very much.
Well, I really want to thank you, Kuda. I just can say to everyone, this is my most Damascus experience of science, and Kuda, you have really, really done it justice with this incredible presentation. I can see you're becoming a giant in the subject, and it's absolutely wonderful. And then just seeing, you know, the evolution of the instrumentation and the detail and everything. And I think you have put the case so well that Africa does need one of these instruments, especially since so many of the samples are coming from our continent. So thank you so much. I think we should take a few talks. This is our science talk, and it's been a fantastic science talk. We should, excuse me, take some questions. You can raise your hand. If there's not a rush on the mic, you can open your mic. Kudo will take some questions. So we're getting a lot of people saying great presentation and great talk, Kuda. Oh, so that's fantastic.
Yeah, thank you very much. Thank you.
There are some mics that have opened. Folks are welcome. It's a rare occurrence to have Kuda on the line here to talk to us, and it would be very worthwhile.
This is Tabitha Dobbins. If I may ask a question, can you, Dr. JAKATA, very nice presentation. Can you give us an idea of the spatial resolution of the current small instrument versus the spatial resolution of the one that's being built for very large samples?
Okay, so I think so for the current one, you can also go to 0.7 microns. That's the lowest resolution that we can go to. Of course, when I showed you the picture of what BM05 looks like at the moment, I showed 2 detectors, but we can actually add in an extra one and a third detector, and that's the one that allows us to go to 0.7 microns.
If I understand correctly, you can take a coarse picture with that very, very big gantry where your big sample is mounted, and then you can click on something interesting inside, and it will make that the new epicenter of rotation and produce a new high resolution tomograph. So you can really navigate around your sample.
Yes, yeah.
In real time.
And if I may follow up, what's the time scale for the high resolution version of the image for a given size, for example?
Sorry, I don't understand the time scale.
How long is the collection time? So say if you wanted to take the entire crocodile at high resolution, how long would that measurement take is what I'm trying to get at. But of course, you would probably choose a smaller region of interest, but I would like to know something about the time scale.
Okay, so about the time scale, it really depends. So it depends on the size and on the setup that you want and what you want to look at. So it's if you just wanted to take something, sometimes when we're doing something at very high resolution and it's something like, let me say about 50 centimeters in length, it could take something like 12 hours. When we put specimens in a tube, for example, and we automate so that we do everything. But again, it's a sample by sample case and what is required. Okay, thank you.
I think this imaging of paleo specimens at synchrotrons has really been a revolution in paleontology. I think even in mindset or culture, because no longer do you possibly damage a sample. Someone once had a talk with micro jackhammers. When you call it preparing a specimen, but you can actually digitally do that. So how would you compare, let's say, the value of the study if you had prepared a sample compared to if you had a very good quality digital tomograph, phase contrast tomograph of that same sample?
I think from my experience, what I would say is there is value in both. So there's a good reason why you don't, we haven't, we still need the mechanical preparation because it helps to reduce. So some of the samples, for example, usually when you bring samples to the synchrotron, it's because you have tried it in a lab source before, and you've seen that actually you cannot get get the quality of images that you need, and that is usually because the sample is too large. So the initial preparation helps you to remove a lot of the pressure around and do the preliminary studies. And even when you bring the sample to synchrotron sources, in as much as you can bring large sizes of specimens, there are still size limitations as well. And so in the end, I think you still need to some form of preparation. I think what I've already seen here is, for example, we were working on teeth, when you want to really focus on a very small feature in a specimen and look at several teeth, it helps a lot when the sample is better prepared to focus on one very particularly small tooth in a very big skull, and then you study so that you get very good images at very high resolution. So in the end, I think yes, there is still value, and I've seen a lot of good quality research that has come out from mechanically prepared samples, which did not need tomography. And but however, technology, perhaps in the far future, it might not be needed.
Yeah, Julian Benoit here.
Yes.
Thank you for the talk. If I may add to your answer.
Please go ahead.
Yeah, well, I think the big contribution of imagery is really to see the internal structure of the fossils, which mechanical preparation can never achieve. And mechanical preparation is always destructive. So what is lost is forever lost with mechanical preparation. While when you prepare a fossil digitally using the CT images, everything is reversible, and I mean there's no risk of any destruction in that particular case. So I think that's the two main points of scanning fossils. It's really first the non-destructive approach, and second the fact that you can see things that you will never see otherwise.
Oh, thank you for that answer, Julian.